Hello everyone from Math 1435. It's Pre-Calculus 2. Professor Winston here again with a video on your KnewtonAlta homework for section 7.3 part 1. This is the sine and cosine values in the first quadrant. So remember the coordinate plane, the xy coordinate plane, and the first quadrant is the upper right quadrant where x coordinates and y coordinates are both positive. And we talked about drawing angles before in standard position. Right, so this is about angles when drawn in standard position that end in the first quadrant, and what are the sine and cosine of those angles. And we're going to talk about some very special angle measures in this section. Okay, so here's the mine says preview, right? This is the KnewtonAlta homework, section 7.3 part 1. Got your mastery bar as usual, showing you how far you've gone in the section. The drop down for all the objectives and your progress on those objectives. There are only 2 objectives in this section, this homework. There's a part 2 for section 7.3. So this objective is find the exact sine and cosine values for angles in the first quadrant of the unit circle. So it's the first time I'm seeing this objective. Now hopefully, before you started this, you read the OpenStax book for section 7.3. You watched some videos that were posted in Canvas there for you. Maybe some other ones in YouTube, and you took notes on your reading and your videos and practiced some exercises. Now hopefully you're familiar with the material before you start the homework here. But if not, if you're still uncomfortable, still don't know what's going on, pardon me. If, I've been saying this every video, when you come across a new objective, I'd recommend just going, hitting more instruction. And I'm going to go to some paper here, because I think the first thing they have here is a video for you on, 30, 60, 90, and 45, 45, 90 right triangles. And finding the sine and cosine and all that of 30 degree, 45 degree, and 60 degree angles. Right? Those are our special angles that you should know the sine and cosine of by heart. All right, so after this is over, I would recommend, or maybe even during this, I would recommend memorizing the sine and cosine of a 30 degree angle, or pi over 6 radian angle, a 45 degree angle, or pi over 4 radian angle, and a 60 degree angle, which is a pi over 3 radian angle. I would recommend memorizing the sine and cosine of those particular angle measures, and it'll make things much easier for you for the rest of the course. So you got this video. Now I'm going to go to a paper here, and we'll talk about these different kinds of special triangles and how they develop, how we can develop an understanding of how to find the sine and cosine of these particular angles. Alright, so I'm starting here. We'll start with a 45, 45, 90. Alright. And this is all degrees. 45, 45, 90 right triangle. And the way I'm going to think about this, a 45, 45, 90, and again, these are just the angle measures of the 3 angles of the triangle. A 45, 45, 90 right triangle is an isosceles right triangle. Alright, so I'll draw up a picture here. Again, this isn't perfect. So it's got a 90 degree angle, and then a 45 degree angle, and then the other one would have to be 45 degrees as well, because remember, all 3 angle measures in a triangle must have a sum of 180 degrees. Right? Now, you may have seen this before in some geometry class you've taken. You've probably seen this before before this course. But if you have a triangle and two angles have the same measure, then the side opposite, right, the sides opposite will be the same length. So this side here opposite this 45-degree angle will have the same length as the side opposite this 45-degree angle. So I'll put the little tick marks to indicate that these two are the same length. Now 90 degrees is larger than these two, so the opposite side, or the hypotenuse, is going to be larger. So not the same length as those other two. And this is what's called an isosceles right triangle, right, where the two legs are the same length. Now, because these two lengths are the same length, I'll say that they're very simply, you could call them x units long if you wish, but when we're talking about sine and cosine and tangent, it doesn't matter how large a triangle is. All that matters is the angle measures, right? Because the sine and cosine and tangent of an angle measure is what we're focused on. So it doesn't matter the size of the triangle. So you could call these whatever lengths you want. Just to simplify things, I'm going to say, let's say this leg is 1 unit long, and this leg is also 1 unit long, right? Again, because it's isosceles, they're both legs opposite a 45-degree angle. All right, and then you can use the Pythagorean theorem. The length of the hypotenuse, remember, it'd be a 1 squared plus 1 squared, right? This leg squared plus this leg squared would be equal to the hypotenuse squared, right? Hyp squared. Well, what's 1 plus 1? That's 2, equals the hypotenuse squared. So the length of the hypotenuse is the square root of 2 units, right? So the hypotenuse here is the square root of 2 units. And now that I have this triangle set up, I can find the sine, the cosine, the tangent, the value of all 6 of those trig functions, those trig ratios, for a 45-degree angle. I just pick one. So let's say we focus on this 45-degree angle, and it really doesn't matter because they're both the same measure. But let's say we focus on this 45-degree angle here. If I focus on this one, then this 1 unit here is the length opposite, right, OPP. This length of 1 unit, this side, is the length adjacent, ADJ. As we've already established, the longest side here opposite the 90-degree angle is the hypotenuse. So now, using this picture with these lengths, we can establish then that the sine of, what angle? This 45-degree angle. Remember, you have to have an angle measure, either the name of an angle or the measure of an angle in parentheses after the name of the function. The sine of a 45-degree angle, remember, it's opposite divided by hypotenuse. So 1 divided by the square root of 2. And there you go. And this is the sine of a 45-degree angle in any triangle, not just this one. All right, any right triangle. So you could triple all these lengths, you could quadruple all these lengths, and the sine of the 45-degree angle would still be equivalent to 1 divided by the square root of 2. Which, if you rationalize, multiply the numerator and denominator by the square root of 2, this would just be the square root of 2 in the numerator divided by 2. All right, memorize this, please. Put it in a box. Okay. All right, and just to make it a little more believable, I'm going to pull the calculator up. All right. And let's turn this on here. Now, make sure I'm in, now this is degrees, right? Make sure I'm in degree mode if I'm doing degrees. So get back to the main screen here, and what's the sine of a 45-degree angle? And you see it's about 0.707106, blah blah blah. That is, if you calculate take the square root of 2 and then divide it by 2, and you get the same value. Okay, so the sine of a 45-degree angle is the square root of 2 divided by 2, or 1 divided by the square root of 2, same value. Okay. And the same thing would go, now that's in degrees. Remember there's also radian measure. So you say the sine of 45 degrees, or the sine of, and remember how to convert from degrees to radians. You would multiply by pi over 180 degrees. This would simplify to pi divided by 4 radians. So you can say one of these two things and they mean the same thing. The sine of a 45-degree angle is the square root of 2 divided by 2. Or you could say the sine of a pi over 4 radian angle, which is the same as a 45-degree angle, they're the same measure, is the square root of 2 divided by 2. And again, please, get to memorizing this. Okay, that's one part. That's the sine. Using the same picture I've established here with this isosceles right triangle, you can also find the cosine of a 45-degree angle, right? Or the cosine of a pi over 4 radian angle, right? Same angle. Now remember this, the cosine of an angle, and again I'm focusing on this 45-degree angle here, it really doesn't matter, but just pick one, is the adjacent length divided by the hypotenuse, right? So again, that's adjacent length 1 divided by the hypotenuse is still the length of the square root of 2. And it's the same thing, rationalize, multiply the numerator and denominator by the square root of 2, and you have the square root of 2 divided by 2. So they're the same. Look at that, they're the same. And it makes sense since the opposite length and the adjacent length were both the same, right? That means the sine and cosine were the same. Right, so the sine of a 45-degree angle, the cosine of a 45-degree angle, or a pi over 4 radian angle, they're both the square root of 2 divided by 2. All right, please get to knowing that, memorizing that. And again, just to make you maybe believe it a little more, I'll pull out the calculator. I'm in degree mode. I'm in degree mode here, so let's punch in this time the cosine of a 45-degree angle. See, it's the same value, right? That's square root of 2 divided by 2, that 0.707 something. All right. Okay. Getting rid of this. And now that we have the sine and the cosine, really you can get all the rest of them pretty easily, right? And then I'll put one more down here. Now this is only 3 of them. Remember there are 6. There's the tangent of a 45-degree angle, or the tangent of a pi over 4 radian angle. Remember the tangent in a right triangle was the opposite length divided by the adjacent length. Well, here's my 45-degree angle in this right triangle. The opposite length is 1, the adjacent length is 1. 1 divided by 1 is just 1. Easy, right? So the tangent of a 45-degree angle is just 1. Right? I'll show you that here. Right? The tangent, and I'm in degree mode. Right? The tangent of 45 degrees, 1. Right? All right. Then, if you wanted the other 3, remember the other 3 were the reciprocals of these. All right, the other 3 ratios. So remember this was the sine of a 45-degree angle. The reciprocal was the cosecant, right? CSC, cosecant. So the cosecant of a 45-degree angle or the cosecant of a pi over 4 radian angle. Just flip this over. Now you can flip this over. make it 2 divided by the square root of 2, but then you have a square root in the denominator. I'm just going to flip this one over, right? Make it a hypotenuse over opposite. That's the square root of 2 divided by 1, or just, the square root of 2. And then the cosine of 45 degrees, the cosine of pi over 4 radians was the same thing. Just flip it over for the secant. Remember, the reciprocal of cosine was called secant, right? The secant of 45 degrees. And just flip over the cosine, and again, it would just be the square root of 2 divided by 1, or just the square root of 2. And this is about 1.414 something, so both of these are about 1.4. And then the reciprocal of the tangent, right, was called the cotangent, right? It was abbreviated COT. And what's the reciprocal of 1? Well, remember, 1 is just the same as 1 divided by 1. Flip it over, it's still 1 divided by 1. So the cotangent of 45 degrees is also 1, right? Same as the tangent. All right, but you're just flipping the fractions over, taking reciprocals. All right, so those are all six of the trig ratios for a 45-degree angle. And then they come from this, 45, 45, 90 right triangle. Okay? All right, so the other special triangle is a 30, 60, 90. Right? And in that triangle, you have a 30-degree angle, a 60-degree angle, and a 90-degree. Right. So 30-degree, 60-degree, 90-degree right triangle. Now the way I'm going to think about forming this, the other one was pretty simple. It was just an isosceles right triangle. All right, the way I'm going to think about forming a 30, 60, 90 triangle is I'm going to cut what's called an equilateral triangle in half. And I'll show you what this is, what I mean by this. I'm going to cut an equilateral triangle. There's a triangle symbol in half to produce a 30, 60, 90. Right. So here's an equilateral triangle. Now hopefully this sounds familiar, equilateral. All that means is it's not a right triangle. Right? It's not a right triangle. It's a triangle in which every single side has the same length. Same lateral side. So every single side has the same length. So I'm going to put a little tick mark on all of them. Not only does every side have the same length, but if every side is the same length, that means every angle opposite is the same. So if all three angles are the same and they have to add up to 180, it means every single angle is 60 degrees. Right. So I have a 60-degree angle showing up 3 times. Now, this is not a right triangle, right? There's not a 90-degree angle in it. So I can't talk about the sine, finding the sine and cosine just yet. But here's what I'm saying up here. I'm going to take this equilateral triangle and cut it perfectly in half down one of the vertices. So I'm going to start a vertex here, say that top one here. And I'm going to draw a perpendicular segment, some segment that's perpendicular to the other side. Cut it perfectly in half. Right. So here's the cut. And then what I create, and I'll just do the one on the left here. I have this. Now I have I actually have 2 right triangles. Right? The one on the left, the one on the right. Let's just look at the one on the left. This angle, so I have a 90-degree angle, right? Because this was a perpendicular cut. So this is a 90-degree angle here. This didn't change, right? This lower left corner. This is still 60 degrees, meaning that this angle up here has got to be 30 degrees. Right. Now let's go back and look at this, this equilateral triangle. Just to make things a little easy for me, because I was cutting things in half and I don't want to see fractions just yet. Let's just say that each of these side lengths was 2 units long. 2 units, 2 units, and 2 units, right? All in the equilateral triangle. Now if I were to cut this in half and then look at the left one, this hypotenuse, right? This side is the hypotenuse here. That's this side here. So that's still 2 units long. This side was 2 units in the equilateral triangle, but I cut it, perfectly in half. So that's 1 and 1. So this side here is now this side here. This is 1 unit long. All right, and then we can use the Pythagorean theorem to find the length of this side. All right, so 1 squared plus x squared. I don't know this other leg, so say x squared must be equal to the hypotenuse squared, 2 squared, right? And I can do this because it is a right triangle. I can use the Pythagorean theorem. So we have x squared must be equal to 3, right? Because this is 1 plus x squared equals 4. Subtract 1, x squared must be 3. So x must be the square root of 3 units long in my triangle setup here. So this side, the height of the triangle is the square root of 3 units. Okay. So now, using this triangle, we can figure out the sine and cosine and all the trig ratios, all 6 of them, for a 30-degree angle, right? Because you see I have a 30-degree angle in this right triangle, and for a 60-degree angle, right? Because I have it's just you have to it depends on which one you focus on, right? So you gotta pay attention. All right, so I'll do that over here. All right, let's take a look at this triangle. Right, forget the equilateral triangle right now. Now I'm focusing on this right triangle. And let's focus on the 30-degree angle. How about for 30 degrees? How about for 30 degrees? What would be the sine of a 30-degree angle? Or what would be the sine of a pi divided by 6, pi over 6 radian angle? Remember how to convert from degrees to radians. Right, talked about that already. All right, so what is the sine of a 30-degree or a pi over 6 radian angle? So notice I'm focusing on the 30-degree angle. So if I'm looking at this 30-degree angle, remember sine is opposite. So opposite length is 1 divided by the hypotenuse is 2. I'll put this in a box. Right, please get to learning this very quickly. Right. So the sine of a 30-degree angle, or a pi over 6 radian angle, is a half. All right, let me pull this up. All right, and I'm in degree mode still. All right. The sine of a 30-degree angle is 0.5, 0.5. That's a half. Okay, and this just came from cutting an equilateral triangle in half to create a 30, 60, 90 right triangle. So if the sine is a half, then the cosecant would be 2. Right? Okay, then the cosine. What's the cosine of a 30-degree angle? Or, the cosine of a pi divided by 6 radian angle? Same thing. All right, again, you're focusing on the angle measure that's 30 degrees. So I'm looking at this angle up here. Remember, that's the adjacent length. So this time the numerator is the square root of 3. It's different. Right, divided by the hypotenuse, 2. Adjacent divided by hypotenuse. So there you go. Square root of 3 divided by 2. All right, let me show you that here. Let's punch it in. The cosine of a 30-degree angle. Again, make sure you're in degree mode if you're entering degrees. If you enter pi over 6, make sure you're in radian mode. is approximately 0.866. Right, approximately 0.866. And you'll see that that is the square root of 3 divided by 2. See, the same exact value. So the cosine of 30 degrees, the cosine of pi over 6 radians is the square root of 3 divided by 2. All right, and then I'll put the tangent up as well. All right, the tangent of 30 degrees, or the tangent of pi over 6 radians. Remember, tangent is opposite divided by adjacent. So there's my 30-degree angle. Opposite, 1 unit, divided by the adjacent to the 30 degrees was square root of 3. And there you go, 1 divided by the square root of 3, or if you rationalize, multiply the numerator and denominator by the square root of 3, it's the square root of 3 divided by 3. Right. And then all you need to do, again, to find the cosecant would be 2. Just flip the sign over. The secant would be 2 divided by the square root of 3, or 2 times the square root of 3 over 3 if you rationalize. And then the cotangent would be the square root of 3 over 1. Right? Remember for the reciprocals. All right, let me just punch in the tangent. See, the tangent of 30 degrees is approximately 0.577. And you'll see that 1 divided by the square root of 3, or the square root of 3 divided by 3, however you enter it, is the same value. All right, great. All right, so that's for the 30-degree angle. Now, what if instead of focusing on the 30-degree angle, and now focus on the 60-degree angle? So now we're looking at, for the 60-degree angle, which is the same thing as, if you convert the angle measure to radians, that was the same thing as pi divided by 3 radians. Right? So this time I'm not going to write both of them when I put in the sine, cosine, tangent. Right. So now I'm focusing on this 60-degree angle. So I'll start with the sine. What's the sine of a 60-degree angle? So focusing on the 60 here, the opposite over hypotenuse. Square root of 3 is the opposite now to the 60-degree angle. So square root of 3 divided by 2. All right, the hypotenuse is 2. And there you go. All right, so again, please know at least know by heart the sine and cosine of 30 degrees, 45 degrees, and 60 degrees. And if you'd like to enter it, the sine of 60 degrees. Remember that square root of 3 divided by 2 was up here. It's about 0.866. Right? See, it's the same value as square root of 3 divided by 2. And what's the cosine of a 60-degree angle, or a pi over 3 radian angle? Remember, cosine is adjacent over hypotenuse. So here's the 60-degree angle. Adjacent now is the 1. Hypotenuse is 2. 1 over 2, 1/2. I'll put that in a box. Important that you remember the sines and cosines of these special angles, 30, 45, and 60. Pi over 6, pi over 4, pi over 3 radians. All right, so see, cosine of 60 is just 0.5, right, when I put it in degree mode. And the tangent, right, the tangent of 60 degrees, and tangent of 60 is opposite square root of 3 divided by adjacent is 1. The square root of 3 divided by 1, or just the square root of 3. All right. And let's double check that. What's the tangent of a 60-degree angle? See, it's 1.732 approximately. And what is the square root of 3? Hopefully it's 1.73. Yes, it's exactly the same. So this is correct. And then the cosecant, you flip the sign, it'd be 2 divided by the square root of 3, and then you can rationalize. The secant of 60 degrees would be 2 over 1, or just 2. And the cotangent of 60 degrees, or pi over 3 radians, would be 1 divided by the square root of 3, right? Flip that over. All right. So again, to recap, To recap these values, please know these values. The sine of 45 degrees, or pi over 4 radians, is the square root of 2 divided by 2. And so is the cosine of that same angle. The sine of a 30-degree angle, or a pi over 6 radian angle, is a half. The cosine of 30 degrees, or pi over 6 radians, is the square root of 3 divided by 2. And then for 60 degrees, it just switches, right? It's the other way around. Sine of 60 degrees, or pi over 3 radians, is the square root of 3 divided by 2. And the cosine of 60 degrees, or pi over 3 radians, is a half. Right. So please, please, please get to memorizing those. All right. Now, one other thing mentioned in the name of the objective was the unit circle. So I'll talk about that real quick, and then we'll get into some actual problems. Right. So they talk about the unit, the unit circle is mentioned. The unit circle is just a circle with a radius of 1. With a radius of 1 unit. And if we're talking about the unit circle on the coordinate plane, right, the xy coordinate plane, typically they mean that the center of the circle is at the origin, right, at the point 0, 0. All right, so if I were drawing a picture here, the unit circle has center at the origin, and then the point 1, 0 would be on it, and then 0, 1, right, and then negative 1, 0, and 0, negative 1. And again, this isn't a great drawing. And then all the points that are 1 unit away from the origin. All right, so something like this. And it's not a perfect circle or anything, but bear with me here. Something like that. All right, every single point. All right, if you take any point here, like this point here. So this point, this point has an x coordinate and a y coordinate, and it should be 1 unit away from the center, right? That's what it means to have a radius of 1. So from the origin here, this distance should be 1 unit. Now the only reason the unit circle is brought up is for when we're drawing angles in standard position. Remember how we draw an angle in standard position. The initial side of that angle is on the positive x-axis. So this would be, the initial side here. And let's say that this pink side, this radius is the terminal side. So what happens here is I got this angle measure. There's an angle. What's called a central angle, because its vertex is at the center of the circle, central angle. And we'll say this angle measure is the letter T for T degrees or T radians. Okay. Now it could be T, it could be theta, it could be alpha. This could be anything, right? But this is an angle measure. Now you can draw a right triangle with this angle in it, right? And it's very simple. So if I start from the positive x-axis and I sweep out this angle of T degrees or T radians and end at this radius here, say I've traveled from here to here, you're at this point. I'm starting at 1, 0. I sweep out this angle. I end at this point on the unit circle. And then what we're going to do, and we're going to do this a lot. You're going to see me doing this a lot in my drawings. I take a point on the terminal side here. And again, this is the terminal side. I take a point on the terminal side and I draw a perpendicular segment to the x-axis. All right, just from that point on the unit circle, I draw a segment perpendicular to the x-axis, right? the horizontal axis, not the vertical. Don't go left or right. I'm going down or up. Right? If I was over here, I'd draw it up. And do you see the right triangle? Right? Do you see the right triangle? Hopefully you do. Now, because I have a right triangle now, we can talk about finding the sine and cosine and tangent of this angle t, this t radians or t degrees. All right, so this leg here, right, from here to here, right, from the origin to here, right beneath the point. That, well, if you go directly beneath a point, that's just the x coordinate of that point. Remember, x coordinate is left and right. And then from here to here, right, going from below the point on the circle upward, well, going up and down to a point, that's the y coordinate. So do you see I have this right triangle where the hypotenuse has 1 unit long, right? The hypotenuse is the radius. Then one leg is the length of x units, the other leg is the length of y units. So do you see how, say the cosine, I'll start with the cosine, you'll see why I'm starting with the cosine in a second. The cosine of this t angle, remember, is adjacent, so x divided by the hypotenuse is 1. X divided by 1, well, anything divided by 1 is itself, so it's just x. So the point that I stop at, the x coordinate of that point is just the cosine of the angle that I traveled, of the amount of turning I made. That's why I started with cosine, because it's the x related to the x coordinate of the point that I stopped at. And then how about the sine of that angle? The sine of this angle t, this t radians or t degrees. Remember, sine is opposite over hypotenuse, so this y length divided by 1, or just y, right? Y divided by 1 is just y. So the y coordinate of this point that I stop at, the y coordinate is just the sine of the angle, the sine of the central angle. All right. So that's why the unit circle is brought up. It's because points on the unit circle, right? So like if you take any point on the unit circle and you draw an angle to get there from the positive x-axis, draw it in standard position, the x coordinate of that point will be the cosine of the angle you drew, of the amount of turning you did. And the y coordinate of that point, whatever point you're at on the unit circle, the y coordinate will be the sine of the angle you drew. Really that simple. Okay. The drawing, maybe making the drawing wasn't simple. I don't know how you thought about that, but how you felt about that. But just remember that cosines are related to x coordinates, and sines are related to y coordinates. All right. So please keep this in mind. This is going to be very important for the rest of this assignment. All right. So now that I've got the cosine and sine of a 30-degree, 45-degree, 60-degree angle out there, showed you, the unit circle, right? Circle with a radius of 1 centered at the origin, and how when you start at the positive x-axis and do some turning, create some angles, you land at different points on the unit circle, and each of those coordinates, right, the x coordinate and y coordinate, will correspond to the cosine and sine of the angle you formed. All right, so let's go back to the website and actually get into a problem. I know that was a lot. All right, that was about half an hour of me explaining. I kind of explained both objectives right now, and I go through more here to show you. See this circle with a radius of 1 they're drawn here, right? This little dotted. This is part of the unit circle in the instruction. See, it's 1 unit away from the origin. But you see how the x coordinate, the horizontal is a half. That was the cosine. Remember the cosine of 60 degrees? The length of the horizontal leg, the x coordinate of this point on the unit circle is a half. And remember we saw that the sine of the 60-degree angle was square root of 3 divided by 2. See how that's the vertical, the y coordinate? And you can read all this, please. Read all this. There's a lot to read. And they do it for, radians and degrees and all that. All right. So question, if the terminal side of an angle theta, this time it's theta instead of t, right? If the terminal side of an angle theta intercepts the unit circle when y equals a half, which of the following could be the angle measure of theta? All right, so I'll pull up my paper here. All right, so they're saying, I'll draw here's the unit circle again, and I'm going to be drawing the unit circle a lot. So again, this is 1 unit from the center, 1 unit, 1 unit, and 1 unit. Okay, and they're saying, the terminal side of an angle theta intercepts the unit circle when y equals a half, right? Here's the y-axis, x-axis. When y equals a half, that's here. So we're talking this point or this point on the unit circle when y is a half, right? A point in the first quadrant, and there's a point in the second quadrant with y being a half. Now this, section 7.3 part 1 is only about the first quadrant angles. So the angle in question here is this angle. And so again, you're always starting from the positive x-axis, always drawing your angles from the positive x-axis. And they're saying that the terminal side, the end of the angle, hits this point on the unit circle with a y coordinate of a half. And then this angle here is angle, they're calling it, theta. So I've got this angle theta that hits this point here with a y coordinate of a half, or the distance going from the x-axis up is half a unit. So remember, y equals a half. I just mentioned when you're on the unit circle, the y coordinate of your point is the sine of the angle that got you there. So this means the sine of theta is a half. Now this is a very special number, a half, right? There was a half, square root of 2 divided by 2, square root of 3 divided by 2 that showed up in my little drawings earlier with the 30, 60, 90 and 45, 45, 90. What angle that I went over had a sine that was equal to a half? Well, the only angle I mentioned earlier with a sine of 1/2 was 30 degrees. Right, 30 degrees. So theta could be equal to 30 degrees. Now there are other angles. We're gonna see larger angles later. So like this angle here that takes me over here to this point with a half. There's an angle, a large angle and an obtuse angle with a sine of a half. But we're only talking about the first quadrant right now. So just the 30-degree angle. Now notice our choices are all in radians, right? They're not in degrees. Remember, 30 degrees is the same as pi divided by 6 radians. All right. So the sine of a pi over 6 radian angle would be a half. If I drew a 30-degree angle, right, or a pi over 6 radian angle, the point on the unit circle that I'd stop at, if I went 30 degrees, right, from the positive x-axis, go positive 30 degrees, this would be the point square root of 3 over 2 for the x-axis. Remember, the cosine was a square root of 3 over 2, and the sine was a half. You'd land at that point on the unit circle, square root of 3 over 2 and a half. All right, so it's 30 degrees. It's pi over 6. All right, pi over 6 when I go enter my stuff here. All right. And again, they go through and they draw a little picture for you. You see a square root of 3 over 2 for the horizontal, half for the vertical, cosine for the x, sine for the y for the angle that's drawn. Right. Okay. And this is the same. I drew your unit circle already, so I've kind of already covered this topic. So I'm not going to click on more instruction. You can, of course you can. But I've already covered this topic about how do points on the unit circle correspond to the sine and cosine values of certain angles, of the angles you're drawing. So now this is not the first quadrant. Notice, the first quadrant's not mentioned here, so this is like all around the unit circle. It just says understand sine and cosine values just on the unit circle, not in, the other objective said in the first quadrant. All right. So if the terminal side of angle theta goes through the point 15/17, -18/17, right? This is a point on the unit circle. What is the cosine of theta? Now I'll do a drawing, right? I'll do a drawing. All right, so they mentioned to us here, again, here's another unit circle. So again, one unit from the center, 1 unit from the center, 1 unit, 1 unit, and a rough circle. So there's the unit circle. Now they're telling us that some angle, this angle theta that's drawn passes through the point 15/17, right? So 15/17 on the x-axis, so that would be pretty close to 1, right? Let's say that's 15/17, and the y-coordinate is -8/17. So going down here, and that'd be a little less than a halfway. Let's say that's there, -8/17. So this point right here, right, this isn't perfect, right? This point right here, this is the point on the unit, and this is on the unit circle. It would be, you could do the distance formula and see that it is 1 unit away from the origin. So 15/17, -8/17. All right, so we're told that an angle that's drawn, so again, you're starting from here, starting from the positive x-axis, and some angle is drawn. Now you could draw it in the counterclockwise direction or the clockwise direction, do a positive angle or a negative angle, and they're saying the end of that angle has this point on it. So it could be this way. I could draw a clockwise angle, that angle there's angle theta. I could draw that angle, or I could have drawn this angle. Doesn't matter, all right? So I'll say or, right? Or that angle. But either way, I've drawn an angle, a central angle, that ends, right, its terminal side contains this point on the unit circle. And if you recall what I was saying earlier, the x-coordinate is therefore the cosine of the angle. So the cosine of the angle that I drew would be 15/17. And the y-coordinate of the point on the unit circle would be the sine of the angle. So the sine of this angle would be -8/17. Right? And it's really as simple as that. Just pay attention, just again, all you have to remember is that cosine for x, sine for y. All right. So again, now this, so what would be the cosine, if this is a point on the unit circle? 15/17. So I'm entering 15/17 as a fraction there. And I think they might, no, they don't really draw it. They just, remember that cosine theta equals the x value of the point where theta goes through the unit circle. Okay. All right, and this is pretty similar. The terminal side, the end of an angle that I draw called theta, intersects the unit circle in the first quadrant at 9/25, comma, y. What are the exact values of sine and cosine? All right, so this one you got to find both sine of the angle and the cosine of the angle. All right, so again, I will draw this. All right. In fact, I'll make this a little bigger. All right. So I'll draw my unit circle. So again, 1 unit from the center, 1 unit from the center, 1 unit, 1 unit, and then a rough circle. Okay, so here's the unit circle. Now it was said that I have this angle theta that ends in the first quadrant, right? It intersects the unit circle in the first quadrant at the point 9/25 for the x-coordinate, Right, so let's say that this is 9/25 here. It'll be less than a half. So not 9/25 for the x coordinate, and then some unknown y coordinate. So there's 9/25 for the x coordinate, some unknown y coordinate, and it's in the first quadrant, and I got some angle theta whose terminal side has that point on it. So again, starting from the positive x-axis, say that this is angle theta here, let's say. All right. Now again, if you'd like, and I mentioned this earlier, I'll be doing this a lot. We can make a little right triangle from this. Right. Take the point on the unit circle, take the point on your terminal side, and just draw a perpendicular segment to the x-axis. And you create a nice little right triangle where this side length, right? This side length is 9/25. That's just the horizontal left-right distance to get under that point. It's this length I don't know, right? Because what's the hypotenuse? The hypotenuse is going to be a radius of this circle, and this was the unit circle. It has a radius of 1, right? So do you see what I have here? I have a right triangle where I know 2 of the side lengths. So I can find the third one using the Pythagorean theorem. All right, so what, 9/25 squared plus y squared, right? The sum of the squares of the legs should be equal to the hypotenuse squared. It should be equal to 1 squared. So this is 81 over 625, and 9 squared over 25 squared, plus y squared should be equal to 1. So then y squared equals, now 1, right? Remember, I'd be subtracting 81 6/25 here. You need a common denominator. So this is 625 over 625, and then I subtract 81 of them. All right. So subtracting 81 be 554. No, not 554. 544. 544. So 544, 625ths. Okay. Pretty sure? Yeah. Add 81 to that would be 625, right? And then take, the square root. So y, right, this leg here of the triangle would be the square root of 544 divided by 625. Now I can do the square root of the numerator and denominator separately. So the square root of 544 divided by the square root of 625. We already saw would be 25. And then we can try simplifying this up top here. I'm just going to see what happens when I enter it this way, because I know it doesn't ask me in the problem to simplify anything. All right, it just says to enter your answer below in an exact value, right? So when they say exact value, that just means don't punch it in your calculator. All right, so let's see what happens here. So I'll go back. Now, remember, they want the sine and cosine, sorry. So this y coordinate is, the square root of 544 and then divided by 25. Remember, the x coordinate of a point on the unit circle is going to be the cosine, right, the cosine of the angle. So 9/25 is the cosine of this theta. And then the y coordinate will be the sine of the angle. So this square root of 544 divided by 25, that'll be the sine of this angle theta. Okay, so those are what I'll enter back here. So now the sine is the y coordinate. All right, so that's the square root of 544. Hopefully it takes this with being unsimplified, divided by, and then 25 in the denominator outside the square root. And the cosine is the x coordinate, right, 9/25. And I'll see if it takes that. And it does. Great. I mean, I know the square root of 544 could have been simplified, and I think they might do it here. Oh, they just leave it that way. All right. Okay. So again, hopefully that picture made sense. And you're going to be doing that a lot in your unit circle. Drawing an angle, drawing a right triangle by, drawing a segment from the point on the unit circle to the x-axis, perpendicular to the x-axis. Right. So another one where it's understanding sine and cosine values on the unit circle. All right, so this time the angle is called A instead of T or theta. Right. So if the terminal side of an angle A has the point, this point is on the unit circle, and you can check, take negative 24/25 squared plus 7/25 squared, and you're going to get 1. Right? This is a distance of 1 unit from the origin. So if the terminal side of angle A goes through this point on the unit circle, what's the sine of angle A? Remember, the sine of the angle that you've drawn is the y coordinate of the point on the unit circle that you stop at. So 7/25. 7/25, the y coordinate is the sine of the angle when you stop at a point on the unit circle, right? Just a point that's 1 unit away from the origin. So pretty simple, that, hopefully. Now you can draw pictures like I did too if you wish, but so this time the angle is called T, right? So it's really no different. Instead of a capital A, or theta, it's T. And if the terminal side of angle T goes through the point, and again, you can double check if you want, make sure that this is actually a point on the unit circle. This point is 1 unit away from the origin. So x squared plus y squared equals 1. You can check that. But it is on the unit circle, right? Just believe it for now. What is the cosine of this angle T? Well, remember, the cosine of an angle is the x-coordinate of a point on the terminal side that's on the unit circle. A point on the terminal side that's 1 unit away from the origin. So the x-coordinate, this 3 times the square root of 10. So 3 times the square root of 10 divided by 10. I don't know why I had the backslash in there. Hold on, let me get rid of that. So the x-coordinate corresponds to the cosine. Right? All right, so this is pretty similar. Again, you saw a problem where one was missing, and I showed you what to do there. You're going to use the Pythagorean theorem to find the missing piece. But in a lot of these, it looks like they give you both coordinates: negative 4/5, 3/5, x squared plus. Just double check: is x squared plus y squared equal to 1? Is this 1 unit away from the origin? And it is. All right. So an angle theta has a terminal side with this point on it. What would be the cosine of that angle? It would be negative 4/5, right? Again, the cosine is the x coordinate of a point on the unit circle. The y coordinate is the sine of that angle that's drawn. All right, so pretty easy objective, that one. And this one, you're talking about special angles. All right. And you're talking about the first quadrant only, right? This is that first quadrant, sine and cosine of angles in the first quadrant. All right, so this is the same kind of as earlier. All right, a very similar problem to earlier. I'll do one more. All right. So it says here, determine the exact values just means don't punch it in the calculator. All right, enter it as it is when you're done finding it. Determine the exact values of the sine of theta and the cosine of theta. Given that the terminal side of angle theta intersects the unit circle in the first quadrant at some point with an x-coordinate of 4/15, and again a missing y-coordinate. All right, so I'll draw this again. All right. So again, the unit circle. I'm just going to eyeball this, say these are all 1 unit away, these points here. And an angle is drawn so that the end of that angle is passing through the point 4/15, and then some unknown y coordinate in the first quadrant. There's 4/15 comma y in the first quadrant. So here's the angle that's being talked about here. Right? So starting from the positive x-axis, now I could draw, a negative one. I could draw a clockwise one. This would be fine, but I'll just draw the smaller of the two. So there's the theta they're talking about. And we know that the cosine of this angle is the point is the value 4/15, right? The cosine of theta is the x-coordinate. All right, well, just like that earlier problem I did, I need to find the y-coordinate. All right. Here's again, drop a perpendicular segment. Draw, see the little right triangle here. Hypotenuse is 1 unit, right? This is a unit circle, so that's 1 unit away from the origin. This is a radius. This distance, the horizontal distance is 4/15. The vertical distance is y. I don't know what that is. Then I use the Pythagorean theorem. All right, 4/15 squared plus y squared should be equal to 1. All right, 1 squared. This is 16/225 plus y squared equals 1, which is 225 225. You need to get a common denominator here because I'm going to be subtracting. So y squared equals 209 225. Right? When I subtract 16 from 225, that's 209. And then take the square root. So y equals the square root of, now the square root of the numerator, I'll leave as the square root of 209. And we should know that, based on earlier, the square root of 225 is 15. So the square root of 209 in the numerator, 15 in the denominator, that would be the y-coordinate. And remember, the y-coordinate is the sine of the angle that's drawn here, right? Of an angle drawn in standard position that ends at some point on the unit circle. So back here, and I'll just do the instructor cheat so we can see it. All right, and submit. And you'll see that the sine was the square root of, where is it? See, square root of 209 divided by 15 that we found. That was the y-coordinate, and the x-coordinate 4/15 was the cosine. All right, and then this one here. Terminal side of an angle theta intersects the unit circle in the first quadrant at x equals 20/21. This is pretty similar. All right, x equals 20/21, and I don't know y. I don't know the value of y. And now if this is the x-coordinate of the point on the unit circle, all right, it says it's on the unit circle, then this is the cosine. The cosine would be 20/21. And then just like earlier, I would find the y-coordinate using the Pythagorean theorem, just like the previous example. All right, so I'm not going to draw this one out. And again, you're going to see different numbers than me. You're going to see different problems in different orders. But the way you do them is pretty similar, right? The way you do them is the same. So I draw a picture, use Pythagorean theorem to find the missing y-coordinate, right? The hypotenuse is 1 unit, right? You're on the unit circle, so you're 1 unit away from the origin. And whatever the y-coordinate is will be the sine there. So I'm gonna do my little instructor cheat so you can just see the answer, and you can verify it for yourself if you wish. Like I said earlier, the 20/21 would be the cosine, and then the missing y-coordinate would be the square root of 41 divided by 21. All right. And I believe that is all. Right. So you know what the unit circle is, right? A circle with a center at the origin. Radius of 1, and if you draw an angle in standard position, right, if you draw any angle in standard position, I'll bring that paper back. You draw an angle in standard position, starting from the positive x-axis, you're going to land at some terminal side, and whatever point on the terminal side is on the unit circle, right? That point, the x-coordinate will be the cosine of your angle, the y-coordinate will be the sine of your angle. All right, and then the one last thing I want you to really remember again is the value of the sine and cosine of those special angles, right? The sine of a 45-degree angle or a pi/4 radian angle, the cosine of a 45-degree or pi/4 radian angle, both of these were the square root of 2 divided by 2. Or approximately 0.707. Right. And then for 30 degrees, right? Remember the sine of a 30-degree angle, or pi over 6 radian angle, was a half, or 0.5. The cosine of 30 degrees, or pi over 6 radians, that was the square root of 3 divided by 2, or about 0.866. And it just switched when you did 60 degrees, right? The sine of 60 degrees, or pi over 3 radians, was the square root of 3 divided by 2, or about 0.866. And then the cosine of 60 degrees, or pi over 3 radians, was 0.5, or a half. And for the 45, for the 45 degree angle, draw, if you don't remember what it is, maybe draw an isosceles right triangle. Draw a 45 to 45, 90 triangle. And for the 30 and 60 degrees, if you don't remember those, maybe it would help if you drew an equilateral triangle and cut it in half like I did. And you might be able to derive the values of the trig functions for those 30 and 60 degree angles from that. All right. So that's it for this. This is section 7.3 part 1. Hopefully it's a good guide for you, help you get through your own homework. Again, you're not going to see the exact same order, the exact same problems that I'm going to, but the objectives are the same, the way I do them, the instruction, all that's the same. All right. And thanks for watching, and have fun working on your own assignment.